Okay, so let us start today's session. And so this segment is based on capacitances in the MOSFET. So we'll first look at the various capacitances that we have in the MOSFET device. So let us look at it later. So let us say this is a MOSFET that I have. So let us say it is an NMOS. So let us say you have applied some VG which is more than VTH. Then we will have a channel of electrons here and some depletion region here, right? So the charge in the semiconductor, so this charge is equals to Q inversion plus Q depletion. But inversion charge is much greater than depletion generally. So we will just assume it to be Q inversion. And this will be equal to capacitance times this voltage VGS minus VTH, right? And I'm writing it in coulomb per centimeter square. Okay. So now what is a capacitance? So in this MOS device we apply a small, so earlier it was biased at, let's say, VG, which was greater than VTH. Now I apply a small signal, small VG, and with that what is the change in this charge? It is change in the charge. So the ratio of, if you look at self capacitance of gate CGG, it will be D, change in the charge at the gate with change in the small signal voltage. So we know gate charge will be equal and opposite to semiconductor charge. So if there is a channel of NMOS here, the equal charge will be at the equal and opposite charge can be assumed at the metal gate. So if we calculate CGG equals to D by dVG Cox VGS minus VT, it will be Cox only, CGG. Okay. So now from where does this this QG or Q semiconductor that we have assumed, where does it come from? So in the MOS device, let's say the drain voltage is not there, or we have not applied any drain voltage yet, but only VG greater than VTH we have applied. So the inversion layer is formed due to the electrons injected from the source and from the drain, right? So it will be equal to okay, so Q SAM equals to Q source plus Q drain, right? So this will imply that CGG equal to CGS plus CGE. Okay. So CGS is the gate to source capacitance and CGD is the gate to drain capacitance. Okay, now let us take two cases. One is linear region and that is saturation region. So in linear region, again, let me draw it again. Source, drain. So in linear region, we apply a very small VD, let's say 50 millivolt. So channel is still intact. There's no pinch off and anything. So the how CGG is defined. So CGG equal to CGS plus CGD, and CGS and CGD are assumed to be equal. CGG by 2 equal to Cox by 2. We already know what is Cox. Okay. Now in saturation, what happens is the channel pinches off, right? So, so there is between gate to source, there is the channel, right? So between gate to source, there is the channel, but there is no channel between gate to drain. So there is only this overlap. So in in saturation, CGS equal to Cox, CGD equal to okay, I have not introduced what is overlap. So overlap is between this gate and this drain, there is a very little overlap, LOB. So this overlap uh, gives some capacitance, that is the overlap capacitance, COV. So here in CGS it will be COV plus Cox, but here in CGD, since there is no channel, it will be COV only. Okay, so here it will also be plus COV. I did not introduce. Okay. So this is the case of strong inversion, strong saturation. Okay. Is this clear, Venkata?
Yes, sir. Yes, sir.
Okay. Okay. So now let us move to the questions. Okay. So, uh, so first question, we have to find the junction capacitance. Okay. So let me first draw. What do we know? So there are some dimensions here. So what are those? So let us say this is my NMOS. I'll draw a kind of 3D figure possible. This is source, this is drain. So the dimensions we know is this is length, this is width, this is the depth of source or drain, and this is the length of source drain junction. Okay. So for NMOS, what is given? L equal to 0.18 micrometer, width equal to 1.8 micrometer, and D is doping here, and A is here for NMOS. To 17 centimeter minus 3. Na is 6.2 into 10 to the power 17 centimeter inverse cube. Depth of source drain is 1 micrometer. Length of source drain is 0.18 micrometer. Similarly for PMOS, L is same. Width is 3.6 micrometer. Na is 1.7 into 10 to the power 17 centimeter cube. And D is 10.9 into 10 to the power 17. And depth and LSD are same. Okay. So what is okay? So junction capacitance. So for junction capacitance, we must know the built-in voltage first. So VBI equals to KT by Q ln na and d by ni square. So I think it is not given in the question, but you can assume ni to be, let's say, 1.5 into 10 to the power 10 per centimeter cube. Okay.
Sir, one doubt here.
Yeah.
In the sheet, it is required to use VT log. Shall we use log or ln here?
No, you should use ln only.
Ln only. Okay.
Yeah, by log I mean they mean log base e.
Okay. Okay. Okay.
Yeah. So you should use ln only. This is the correct form.
Okay.
Okay. So okay. So I think KT is, this is VT and it is given to be 26 millivolt. So VBI will be 0.026 ln Na and D by Ni is 1.5 to 10 to the power 10. So if I calculate it for NMOS, I should get, I think, 0.858 volts, and for PMOS 0.892, 0.893 volt. Now what is the junction capacitance? So Cj equals to Cj naught divided by 1 plus Vr by Vbi. So what is Vr? Vr is the reverse bias voltage. Okay. So, and what is Cj naught? Cj naught equals to epsilon Si Q Na and D divided by 2 Na plus Nd into Vbi. So Vbi we know, and all these values we know. So we just need this Vr. We need to identify what is the reverse bias voltage. So let us see now what are the given conditions so that we can identify the reverse bias voltage to find this Cj. Okay. Oh, one more thing here to note, that is all these are in farad per centimeters. Okay. This is farad per area. So if Na and Nd are in uh, per centimeter cube, and you take epsilon Si also in centimeter square, uh, then you should get this as farad per centimeter square. So we should take area also in centimeter square. And for silicon, what should be the epsilon Si value? That is epsilon Si equals to epsilon 11.8 into 8.85 into 10 to the power minus 14 farad per centimeter square. So if it is in okay, okay, for centimeter units, you should use this formulation of epsilon Si. Okay. Yeah. So we have the formulas. Now what we need is, we need area and we need Vr. So let us first talk about Vr. So what is given is, we have this circuit and we know what is the voltage at the output. So it says X bar is 0.9 volts. So here it is 0.9 volts. Okay. So we know here it is 0.9 volts. So let's say its body will be connected here. This PMOS, this is NMOS. Its body will be connected to ground to 1.8 VDD. So if we draw, let's say the drain side, let me draw the drain side. This is drain, and it is 1.8. Let's say for NMOS, output is at drain, right? So this is drain, this is source, this is drain, this is source. For NMOS, output is at drain, so output is at 0.9 volt, and the body is connected to ground. And this is N type, this is P type. So the reverse bias is 0.9 volts. For PMOS, drain, body, and their body is connected to 1.8 volt, and drain is at 0.9 volt. And for PMOS, this is N type, this is P type. So the reverse bias voltage is again 0.9 volts. So for both the cases, VR is 0.9 volts. Okay. And now the area. So what will be the junction area? So if we see, we have the junction is this, right? This is the junction, and so if we see it's 3D image, let us try to look it at 3D. So this is kind of, let's say, 3D. So what will the parameter? Let's say this is drain. So what will be the parameter of the drain? This whole thing will be the drain parameter of the drain. That is, this is the length of a source drain, and this is the width of the device. Perimeter LSD into width, and this is the depth. Okay. So to contribute the area from all these sides, it will be, so from all the four sides. So this side, behind this side, this this side, and this side of the rectangle. So what we will get, the area will be perimeter into depth. So LSD into W into DSD. And one more thing that is remaining is the area of the bottom face. So at the bottom there is also the junction the uh, between the drain and the body, right? So it will be again area of the junction, that is LSD into width. This is the total area. So let me just put some values. So LSD was 0.18, area equal to 0.18 plus, this is parameter, now it is 2L plus 2. It is 2 times 0.18 plus width is 1.8 for NMOS micrometer, depth is 1 micrometer plus again 0.18 into 1.8 micrometer square. So we should get area in centimeters square, and I have calculated it. It comes out to be 4.284 per centimeter centimeter square into 10 to the minus 8 centimeter square. Yeah, for NMOS. For PMOS, it will be only 2 times of this, 208 into 10 to the minus 8 centimeter square. So for PMOS, we just have to change this with this 2 times. With here it is 1.8. In PMOS it was 3.6. So this will be the area for PMOS. So now we have area, we know the reverse bias voltage, we have epsilon, we can calculate this CJ0 and CJ. Then we will get for NMOS and PMOS, and we can add it to get the final answer. So I've not calculated it, but I'll write the final answer. Finally, we get Cj equal to, let's say, Cjn plus Cjp 9.18198 into, okay, 10 to the minus 15 farad. Okay, after multiplying it with area also. Properly. Into area of Nmos plus Cjp into area of Pmos. This is the final answer that we get. Any doubt in this question?
Okay, sir. Okay.
Okay. So in question 2, uh, question 2 is same, only what they have given is uh, the input voltage is, so the bias is different, so input is at 0 volts. Okay, so we have an inverter actually. So input is a 0, output will be at VDD. VDD is 1.8 volt given. So we just have to identify what are the reverse bias conditions. So let us take NMOS again first. This is the drain. Output is 1.8. Body is at 0. So we are equal to 1.8 volt for NMOS. For PMOS, so drain is at 1.8 and body is also at 1.8. So we are equal to 0. So for NMOS, Cj equal to Cj naught by 1 plus 1.8 by VBI, and for PMOS, Cj equal to Cj naught, because we are equal to 0. Okay. So nothing else will change in this question, only the value of VR that we had to identify. And final answer, let me see what is the final answer. So final answer is Cj equal to 11.5 femtofarad. Yeah, this is the final answer. Let us see the next question. Okay. The same circuit as before, Cox is this, and for both PMOS, and width of the devices are same, overlap capacitance is given this, X is at 1.8 volt. Okay, so now what we have is, this is 1.8, so output will be at 0 volt. Okay, so in this case, NMOS and PMOS, so PMOS is off, NMOS is on. Okay, so if you see the region of operation, so for NMOS, VGS n equal to 1.8, VDS n equal to 0. For PMOS, SG equal to 0. So it is off and it is on, but it is in linear region. Right. So, okay. So what do we have to find here? We have to find the capacitance looking at the input, that is CGG only. So we have to find CGG, let's say. So I told it first that CGG equal to CGS plus CGD. Okay. Okay, for both NMOS and PMOS, so CGSN, CGDN plus CGSP plus GDP. So, okay, so for NMOS, uh, we know CGG will be okay in linear region, right? So NMOS CGS will be CGD will be half COX plus COV. For PMOS, since PMOS is off, so there is no channel. So CGS equal to CGD is equals to COV only. Okay, so let's check CGOV. CGOV. Okay, so CGG what we will get equal to CHS and CGS and CGDP, that is 1 by 2 COX plus COVN plus 1 by 2 COX plus COVN. Then for PMOS that is COVP plus COVP. So COX is given and COV is also given, I think. And let me check. So COX is given in farad per micrometer square and COV is given in farad per micrometer. So to find, so you will need to multiply this by area. Okay. So COX, let's say COX and write it in. COX n will be COX dash that is given in question per area into area of NMOS. So that is just L into W that were given in the first question, and COVN will be COVN dash that is given into width of NMOS. It is given per length, right? Check. Yeah, per per micrometer, not per square micrometer. So that is why we will just multiply this by width, and this we will multiply with length and width both. So is this question clear?
Sir, what is the difference between COX prime and COX?
So COX prime is per unit area, and COX is when we have multiplied it by area.
Okay, okay.
So this COX prime is per unit area, let's say per centimeter square, and this COV prime is per let's say per centimeter or per micrometer. Like these are the values that are given in the question. So if I write here, this is COX prime and this is COV prime. So when I multiply with area, so COX will be COX prime into area, and COV will be COV. Okay, COV will be COV prime into width. Okay. Any other doubt?
Okay, okay, sir.
These capacitances are clear, right? So why in linear region, why this is this, and why when it is off, it is only COV. Should I repeat that?
No, no, sir. No, okay, sir.
Okay. So let us look at next question. Okay. We have to find the capacitance. So okay, again we have an inverter. Output is at 0.9 volts and input is also at 0.9 volts. So at this operating point, GM is 3.2 millisiemen, and everything else is given. We have to find the input capacitance. Okay. So Okay, so let me first tell the Miller's theorem. I think it's stated here also in the questions starting itself. So in Miller's theorem, so where does this come into place when we have, let's say this is NMOS, this is output and input, right? So when there is anything that is coupling between output and input, let's say this is CGD. So this is generally resolved. How this is resolved is as we can assume it to be, let's say this is gain times CGD, or what is it, 1 minus A times CGD, and here it is 1 upon 1 minus A times CGD. So this coupling capacitance between input and output is resolved as 1 minus A times A, where A is the gain of the circuit, times CGD at the input, and 1 minus 1 by A times CGD at the output. So this is Miller's theorem. So we will use this to solve this question. So first of all, we need to find the gain. So what is the gain of the CMOS inverter? Let us try to find that out. This is V out. So let's say we apply a small signal V in here, we get a small, say, V out here, ground. This is source, drain, drain, source. Okay. So again, we will do the same thing, that is, we will write the small signal equation of the current. Let's say so IN equal to GMN V in. So VGS is V in plus GDN V out, VDS is V out, and IP equal to GNP minus V plus minus V out. This is VSG and VSD. Okay, so IN equal to IP. So that means GMN V in plus GDN V out minus GMP V in minus GDP V out. So V in GMN plus GMP is to minus V out GDN plus GDP. So V out by V in equals to minus GMN plus GNP GDN plus GDP. And in question they have given RO, I think, yeah, they have given RO of N and ROP. So in that terms it will be minus GMN plus GNP 1 by RON plus 1 by ROP. So it will become minus GMN, put it here, plus GMP into RON parallel ROP. This is the gain. Okay, so now we have found out the gain. So the next step is, so we have to find the input capacitance. So again, let us see the circuit that they have given is apply 0.9 here and 0.9 here is the output. So if you see, if it is 1.8, so VGS n equal to 0.9, VGSP equal to V, so VSGP equal to 0.9 volt, VDS n equal to 0.9, VDS ESDP equal to 0.9. So obviously VDS will be greater than, much greater than actually VGS minus VT. 0.9 minus, if VT is let's say 0.4, it will be much greater than VDS. So these both are in strong inversion, or I should write such strong saturation. And we have seen that in strong saturation that CGS uh, equals to COX and CGD equal to COV, right? So for NCG, CGD, and similarly for PMOS, CGSP equal to COXP, CGDP equal to COVP. Okay, so now let us see all the capacitances that at the input that we have to worry about. So this is gate, this is here, this is here. So there will be one CGD here, CGDP, CGD, and okay, and one CGS, 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 okay. So we know that total CN equal to CGSN plus CGSP plus C. Okay. Now, if we resolve these, how to resolve this? Let me take it an image. So if we resolve this, what we will get? So at its gate, so this will be virtually like ground for small signal. This is also ground. So we can directly take at the gate. We can take. Okay, let me draw a common gate. It is inverted. So at the gate we will get CGSN and CGSP. Now these capacitances, the drain capacitances, we saw that they will be, since they can have input and output, they will be can be resolved by the Miller theorem. So we can get one more, 1 minus A times CGD n plus CGDP, right? So our total Cn equal to CGSN plus CGSP plus 1 minus A times CGDN plus CGDP. So it will be CGS and CGSP is COXN plus COXP plus 1 minus A we calculated. So what was A? This is A. Let me write it there. So it will become 1 plus GMN plus GD GMP parallel RO1, not a parallel, into RO1 parallel ROP multiplied by COVN plus COVP. So this is the final formula that you have to use for Cn, and we have to multiply Cox and these by the area of AN and AP, and these by the widths WN and WP. We should get the final answer as, check. Final answer is C equal to 304.83 femtofarads. Yeah. So Any doubts in this part?
No, sir.
Okay.
Sir, is it required to use epsilon SiO2 anywhere?
Uh, no, because I think all these values are already given. Yeah.
Okay, okay. In any sir, if in any of these problems, if it is required to use permittivity of the
In first,
silicon dioxide,
yeah. No, not silicon dioxide, or silicon only.
um, okay, okay. If it is required, what is the typical value we need to consider, sir?
Okay, let me tell you the value. So I think it is 3.9 into 8.85 into 10 to the power minus 14.
Okay, okay,
So this factor is 3.8 or 3.9 for SiO2, and for Si it is 11.8 or 11.9.
okay, okay,
Generally this factor is 4 times for Si2
okay, okay.
than Si. Okay. So okay, this question. So before solving 5 and 6, let me look at one more question that is a little easier. Okay. So in this question, uh, we have been asked what is the pole at the output impedance. So we have to look at here and tell what is the pole. So at this circuit, at this node, pole will be 1 by RC simply. And R, let me take a new page. Pole equal to 1 by RC. So this is RD is the external resistor. We will have the drain resistance, let's say RO, or here it is given as RDS. The rest, the output impedance of the drain, that is simply nothing but 1 by GD. Anyways, so this RDS is given in the question already. RD is given, CD is given. So pole simply will, so R will be RD parallel with RDS, that is RD RDS by RD plus RDS. So pole to 1 by RC equal to plus RDS by RD RDS into 1 by CD. So that is the only capacitance at this node. So this is the pole that you will need. Yeah. So its value will be minus 95.349 minus. Okay. Mega radians per second. So here also this value is given. These two are also given, so you can directly calculate this. Okay. Any doubts in this?
No, sir.
So let us come back to these questions. Okay. So what we have to find is the FT. Okay. So first, what is given? We have been given, let's say this is I. This is I out. So this is kind of, let's say, short circuit configuration. So this is connected, and ID equal to again mu Cox dash by 2 W by L VGS minus VT whole square. VDS is much greater than VGS minus VT. Strong uh, saturation. CGD equal to COV because of this saturation. W is 10 micro, L is 0.18 micro. Mu Cox dash by 2 is 0.17 millisiemens per volt. Cox prime is 8.5 femtofarad per micrometer square. Overdrive voltage is 0.26 volt. COV is 0.05 femtofarad per micrometer. Okay. FT is the frequency where I out by I in equals to 1. Okay. So to find that, okay, so let us again draw, I'll copy this. So we look at the capacitances. Here will be CGS, here will be CGD, right? But since both are shorted, so it will be same, and we can get this, let's say VGS equal to IN by, so this IN current will divide between this, through this and this. It cannot go into the gate, it will go through there and here. So the voltage here will be V equal to IR. So R, so instead of R we have capacitance, so by S CGD plus VGS. Okay, so this is the VGS, and okay, so now let us try to write the current equations again. Let ID current is flowing through here, so ID we know GM VGS plus GD VDS. So here drain and source are shorted, so VDS is 0, so it's simply GM VGS. And if we see what is ID, so ID is current through this branch plus I out, right? So ID is I out plus current through CGD. So current through CGD is I in to SCGD by SCGS plus CGD, right? So okay, so if we write I out equals to ID minus I in into SCGD by SCGS plus CGD, and we know this ID is GMVGS. GMVGS. So let me copy it. And we know we calculated VGS only, it was I in by SCGS plus CGD minus I in by into SCG CGS or CGD to CGD, sorry, CGD CGD by CGS plus CGD, so equals to GM minus SCGD by CGS plus CGD. CGD. So I'll just put this I in here. So this is I out by I in, the current gain, short circuit current gain. Why I'm calling it short circuit? Because we had shorted the drain and source. So Ft is defined when I out by I in modulus equal to 1. So we need to take its mod and equate equal to 1. So I think okay, I'll not do it completely. I'll give some hint how to do that. Take its mod equal to 1. So S we can put as simply j omega. So Gm minus j omega CGD by j omega CGS plus CGD mod equal to 1. So how to take the mod? So this will simply be whole square. So it will be under root Gm square plus omega square CGD square equal to minus or plus, I don't know. Uh, minus omega square CGS plus CGD whole square. Okay, so this we will get by taking mod, then take the whole square again and solve for omega. So you will get omega t as, let me write it directly, Gm by CGS under root 1 plus 2 CGT by CGS. This is the omega t frequency, and Ft is simply 1 upon 2 pi omega t. Omega t. Okay. So again, everything is given. So even these two are given, Gm is given, I think. We can find Ft, and the answer will be this will be the answer. Okay. Any doubts in this part?
Okay, sir. No, sir.
So next question is in the above calculation, uh, if gate length is decreased, what will be, how will Ft change? Okay. So we saw, let us take it back. So to simplify this, what we can do is, let's say we know that CGS is approximately equal to Cox and CGD to COV. So CGS is much greater than CGD. So we can ignore this CGD by CGS. So it will, Ft can simply be assumed as Gm by 2 pi CGS. Okay, so now we have to see on we just have to analyze how Gm changes with length and how CGS changes with length. So Gm is nothing but del ID by del VGS. So it is just 2 mu Cox W by L VGS minus VT, right? So Gm so if L decreases, Gm increases. Okay, and CGS is Cox into W into L. So if L decreases, CGS decreases. So now if we look at Ft, so if L decreases, Gm increases, CGS decreases. So ft, if this is decreasing, this is increasing, so ft should increase, right? So ft will increase. So g, let me write uh, gm is proportional to 1 by l, cgs is proportional to l, so ft equals to 1 by l square. So this is how ft will change. So if l is from 180 nanometer to 65 nanometer, uh, l is reducing by 2.77 times. So ft will uh, increase by 2.77 square times. ft increases by 7.67 times. So we just have to multiply 7.67 in previous ft and we will get new ft as 360.49 gigahertz. So I hope this is also clear. And is there anything? One more question. Let's see. So we have the same circuit, I think. Okay. So they are saying there is some RS here. V in is given, and we have to find RS 79 ohms. RDS is infinite. The location of the pole is due to the short circuit current. Okay. Okay. So again we have to find the pole here, and it will be again 1 by RC. So here it will be, what it will be the impedance here, it is okay. At the source we get 1 by GM, I think. Yeah. So 1 by R will be 1 by, sorry. So R will be 1 by GM parallel RS, and C is CS. So simply pole is 1 by RC equals to 1 by GM plus RS by 1 by GM RS into 1 by CS. So we cancel GM. So we will get 1 plus GM RS by CS RS. It will be negative. So this will be the pole. Right, the minus 1 by RC. In previous question also it was minus 1 by RC. So this will be the pole that we will get in question 8, and answer will be minus 6481.01 mega radian per second. Is this clear?
Yes, sir.
Okay. So question 9 and 10 I have not solved yet. So, but it is simple. So what you have to find? We have to find. Okay. So we have to find again the pole at the output here. So for that there are two methods. First is you can find the complete transfer function. So to find the complete transfer function, you can take like the use the Norton method. This is the method that sir teaches in the videos, or you can use the my method, that is simply by equating the current. So let's say if current flowing is I1, so I1 will be this current plus this current plus this current. So by solving all these current equations, you can get uh, V out by V. Then you can see what are the zeros and poles in the circuit. So in that way you can find out. Or another way can be like, if you know the okay but you do not know the game, so then so for this CGD, what, let us see the values. If CD is 1.3 pico on CGD, okay, we cannot ignore CGD. Fine, so you will have to find the transfer function itself in this question. Or yeah, we can do one thing. Okay, so we know this CGD can be rectified here as we are concerned with this node, right? So it will be 1 minus 1 by a times CGD, and here it comes as 1 minus a times CGD if we shift it here and there. Okay, so we are only concerned with this part. So if we see 1 minus 1 by a times CGD equals to a minus 1 by a times CGD, you can assume it to be a by a only. So a by a times CGD, that is simply CGD. So now we will have RD, let's say some RSD, CD and CGD. Should be should be out. Okay, so now pole is simply 1 by RC. R will be RD parallel RSD, RDS, sorry, RDS. And C will be simply CD plus CGD. Okay, so in this way you can find the pole here. Sorry, negative sign here also. So let me just try to write it. What you will get, pole will be RD plus RS divided by RDS CGD plus CD. So this will be the pole finally. And for the last question, what is the zero because of the short circuit current? Okay, so for short circuit again, we will short the output and input. Sorry, yeah, the output terminal, that is we will short the source and just post it. So we will short this and this. So this capacitance will get shorted, so it will be zero, useless. The current through this path will be, okay, one current will be ID, that is simply ID is GMVGS, and this another current will be this. So another current will be VGS into S times, call it I2. I2 equal to VGS into S times CGD. So I short circuit will be uh, GB minus GMV. This is going to like this. Input to output. So this is I short circuit. Okay. So the zero will be simply at, okay, if we take ISC by V, we will get SCGS minus GM. We equate it to 0, we will get S equal to GM by CGD. 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 This will be the location of 0. And we will get the answer as 2666.6 mega radian per second. Okay. So we have solved all the questions today. And do you have to ask anything?
No, sir. Everything clear.
Okay. So let us close for today. And if you do get any questions, you can email me or write in the YouTube link. Okay. Thank you.
Thank you, sir. Thank you.